Good morning, good afternoon, good evening, wherever you happen to be in the world today. Welcome to all. In today's talk, we will be learning how to easily deploy confidential computing, sponsored by the Snea Cloud Storage Technologies Group. Joining us today is Steve Van Lare. Steve is the VP of Engineering at Anjuna Security. He has led enterprise development teams for the better part of the last 30 years, including AI and security applications, and has experience at large and small companies like 41st Parameter, Experian, and Oracle. Steve, could you please say hello?
Hi, thank you, Michael.
Awesome. Also joining us is Anand Kashyap. Anand is the co-founder and CTO at Fortanix. Previously, Anand was a security researcher and engineer at Symantec and VMware. Anand holds a PhD in computer science and has done extensive research in computer networking and security. Anand, could you please say hello?
Hello, thanks, Michael. Great to be here.
Awesome, thank you. And I'm Michael Hoard, storage planner at Intel. Today, however, we are wearing our Snea hats to provide educational material to raise awareness on how to easily deploy confidential computing. As a reminder to folks who may not be familiar with the Storage Networking Industry Association, we are an organization of industry-leading contributors focused on promoting education and technical standards around storage and related usage. We have over 180 active organizations, 2,500 individual contributors, and over 50,000 IT end users and storage professionals who rely on the organization. You can learn more at the link shown here and follow us on Twitter. The Cloud Storage Technologies Group within Snea is focused on education to raise awareness of important topics like cloud storage, data services, orchestration, AI, and security, as well as related data processing models, including storage-defined, software-defined storage, Kubernetes, and hyperscaler practices. The CSTI accomplishes this through webinars like this one and collaborating with other industry associations to help build the right understanding and requirements among the standards community. Okay, this is the Snea legal notice, and I'm not a lawyer of any kind. So this is for anyone who wants to refer to content within the webinar. Please read the notice. In summary, it says it's all on you, and please use at your own risk. This also says how to refer to Snea copyright material. Okay, now let's jump into our agenda. Today, we're pleased to have two industry leaders contributing to make confidential computing a reality with capabilities available right now, as we'll see in the video demonstration portion of the webinar. The two companies have different ways to accomplish the problem, so we will hear two perspectives on each of these agenda items. To help deliver all the content, we would like to take questions at the end of the webinar, but please enter questions throughout the entire session because we're eager to get your input. Also, please download a copy of the slides through the attachment icon that's at the bottom of your screen. Without further ado, Steve, please take it away.
Thank you, Michael. Hi, I'm Steve, and I'm happy to be here with Anand. And today we're going to talk about how easy it is to deploy your applications into the confidential cloud and what advantages that has for you and your security. So I want to start by talking about why Anjuna is in this in the first place. Our two founders, Eyal and Jan, were both in the Israeli military. And they realized that as a world, we're really good at secrets. There's lots of secrets everywhere, but we're not very good at keeping them as a general means. So in the military, they had the problem of trying to keep data safe in insecure areas, and they were never able to solve that problem satisfactorily. After the military, Eyal, our CEO, worked at OpenDNS, where he was focused on helping businesses solve some of their key business risks from a security point of view. Jan worked in a couple of different places, then eventually got his PhD in cryptography and security at Stanford. And he realized while he was there that models existed, that the latest CPUs were bringing forward trusted execution environments. And the problems that they had back in the military, the problems they had at OpenDNS were solvable, but there wasn't any real world support for solving these problems. So they recombined forces again and they formed Anjuna with the idea of helping get secure enclave technologies released so that you could, in fact, confidentially run your applications on untrusted hardware and successfully take advantage of these models that now exist and leverage them at economies of scale. So the first thing before we get too deep into this, let me define what confidential compute is and why it's easy for the enterprises at this point in time. Confidential cloud is software. It's software that enables you to take advantage of the confidential compute hardware that now exists. With it, data is protected by default and has a controllable life cycle. So you can control the security of the applications and the security of the data independently of the security of the machine. With it, you can eliminate excess data leakage by essentially eliminating the attack surface that the bad guys go after in terms of extracting information out of applications where the threat is. And using this, it allows you to use the public cloud. You can use any public cloud. You can use on-prem, get the advantages of the latest hardware, get advantages of the economic model of the cloud, and take advantage of it today with what we're doing. So it changes fundamentally the way an organization can manage its data posture without disrupting the processes or the applications that you use today. I talked a little bit about threats. Let me dive into this a little bit deeper. So what confidential compute does is confidential compute allows you to encrypt, isolate, protect individual processes separate from the machine that they're running on, so that I can now protect a thread and I can protect that thread or protect that process, protect that application from other things that are going on the machine. And so this allows you to decouple the security premise of the machine from the security premise of the applications. They can be different things at this point. So from a bad actor point of view, if somebody gets root access to the machine, you're usually considered game over. Once somebody has root, they can get access to anything on that machine that they wish to get access to. With confidential compute, that's no longer the case. So if a bad actor gets access to the root of the machine, the hardware will protect the processes that are running in trusted execution environments. One way I like to think of this is virtual machines were essentially created to protect malformed applications or poorly performing applications, protect the application environment, the OS, and the machines from those applications. Enclaves turns that relationship around. Enclave makes it so you can protect the applications from bad things that are happening on the machine. This also allows you to reduce the number of people that have to be in the circle of trust. So you don't have to cast as wide a net on insiders. Just because somebody has to do some maintenance on the machine does not necessarily mean they should have access to the data or the applications that are running on the machine. So not only can you protect against bad actors, you can protect against insiders that you don't want to be part of the circle of trust. You can protect against malware. Malware obviously can still infect the machine and it can still infect the operating system. But since you've put a barrier around your application is essentially protected from that malware. One of the things that you do with a trusted execution environment is you bring in a set of code, and then you measure that code to make sure it was an unmodified version of the code, that it was the same code you intended to run. And that shuts down a lot of the doors that malware uses to infect applications, modify source, modify binaries, and get into your applications and get into your data. You can protect from horizontal attacks. You can put part of your application in one trusted environment. You can put a part of your application in another trusted environment, and you can build a relationship that they can't communicate unless they can prove their identity and prove that they're running in trusted environments. So if somebody tries to come in through the same port and access the same information, but can't prove that they're a trusted piece of code running in an enclave, you can shut that communication down and the application doesn't see it and the attack doesn't exist. Unauthorized data access, again, since you no longer have to give access to the machine to everybody, people that might snoop on the data, whether it's trying to interface into the file system to get access to your files, whether it's modifying the memory to try to get access to that, you can protect from those threats. So confidential compute protects against a lot of threats that traditionally have been very hard to protect against. And in short, you can go from open computing, where everything on a machine has to be trusted, to zero trust computing, where you don't have to trust the machine. You're focused just on the security for your application. So let me work through a couple of examples for you. Obviously, anything with security, you're going to expect organizations that have a high security profile to be interested in this. And sure enough, there's a lot of activity and interest in confidential cloud in governments, in financial systems, and in medical institutions. But I'm going to talk first about one of the governments that we're working with. And what they're doing is they're moving thousands of sensitive applications into the cloud. And they're moving the infrastructure into trusted execution environments. The applications by themselves are relatively unmodified. If you've got a three-tier application, that three-tier application is going to run in a series of components. You'll link them together and allow them to work as they do today, but without the cloud or without insiders or anybody with access to the machines to have access to those applications. One of the keys to this is the government is managing their key structure essentially on-prem and using those keys so that when you launch a new application or when you launch an application, it needs to prove its identity. It needs to prove that it's been unmodified and it's running in a secure space before you give it keys to access data and do what it needs to do. To the outside world, these applications are all working and functioning unchanged and unmodified. So we're helping this government, like I said, move thousands of applications across to the cloud, and we can support them in whatever cloud they choose. All of the clouds today offer capabilities for confidential compute in terms of what we can do. So this gives them a opportunity to leverage the economics and leverage the systems that exist in the cloud without having to modify their applications. It's essentially a lift and shift in bringing them across. Another important example, fintech, we're working with a bank that's doing something similar. They're doing some of their processing for transactions and some of their scrubbing of information. They're moving that from on-prem to in the cloud. The key management they're keeping on-prem. They want to secure the keys in a central place that they control, but they're not releasing keys until the trusted execution environments say that it's okay to do so. So they're operating in a fairly hybrid mode, but they're running some very complex AI jobs. They're using Kubernetes to deploy the application across the infrastructure that they're deploying across. And the confidential compute platform seamlessly supports all of this. The technology is infrastructure technology that's added to the containers that they're deploying in their pods. And those are then being distributed by Kubernetes. And the workload, as each of these nodes comes up and runs, it validates its identity, it proves who it is, it fetches the keys it needs, and then it's secure and it can do what it needs to do. So essentially, they don't have an HSM anymore. They're using other tools to manage their key environment. In this case, it's HashiCorp. And they're able to leverage a very large set of business applications inside the confidential cloud and make that construct work for all the applications and the components of that application that they're putting in place. So I've talked about a couple of examples, and I've made some claims about this. And I think what I'd like to do next is I'd like to do a demo. And what I'm going to do is back up some of these claims I've made with a very simple example. I'm going to use a command line example in this demo. And the point of using the command line is so that you can easily see how the memory protections work, and you can easily see how the file protections work. So we're going to take an application. I'm going to run it one way, show how it works, and then we're going to put it into the confidential cloud, and we'll try to attack it as an attacker might, and then show what you get from using the confidential cloud and how easy it is to do. Let's take a look at the confidential cloud in action and see how protecting applications really works. I'm going to start an application in a normal environment and show some threats. Then we'll run the same application in the confidential cloud and show how easy it is to eliminate those threats. Redis is a very fast in-memory database. I'm going to launch it from the command line of the server that I'm connected to. Once it's running, I'll put some data into the database. So we'll add Musk's social security, his address, and we'll use this as some sample PII. Now I will do a memory dump of the Redis process and grep the resulting data. And sure enough, we find in the data his name, social security number, and address, all in the memory of Redis available to be viewed. When I terminate the process, Redis will persist the database into a file. And if I read the contents of that file, all of the data is there as well. So now let's see how easily we can protect both the data at rest and the data in use using the confidential cloud. I will launch Redis with the same command line we used before, but this time I will prepend the command line to call Anjuna's software. Anjuna's software will create the enclave and then load the unmodified Redis application into that enclave. Even though the application is now in an enclave, the interface to the application remains the same as it was before. So I'll load the same PII into the database exactly the way we did it before. Then I'll also do the same memory dump that I did before. However, when we do the grep, no data is found, as the memory was all encrypted in use, and there is no clear text available for grep to find Musk's name, address, social security number. It's all been protected. When I stop the Redis process, it writes an output file just like it did. But when we look at the contents of the output file, this time it's all just encrypted data, as we've encrypted it transparently for the application. What we were able to demo today is that by using this unmodified Redis instance and using the confidential cloud, we were very easily able to secure the application by encrypting the memory at use and the data at rest. Great. So I hope that helped highlight some of the confidential cloud, how it works in practice and how easy it is to use it. Essentially, we just added Anjuna run in front of the command line, and you do this whether you're in a Docker container, you do this whether you're running from a command line, and that launches the trusted execution environment, and then you launch the application into that trusted environment. And from there, the policies that you set up beforehand then enforce what's the security perimeter for your process, for your application, for the thing that you're going to present. And this works in any of the clouds, and this works on lots and lots of different applications. And it is absolutely worth spending effort to take a look at this and understand how it can help secure your applications better. So with that, I'm happy to introduce Anand, who is going to take it away and talk about their solutions and how this helps the world.
Thank you, Steve. I think Steve has laid out really well what's the threat vector for applications running outside confidential computing and how those applications can be protected when they're ported and brought inside a confidential computing environment. At Fortanix, and I'm one of the co-founders of Fortanix, we started the company on the foundations of confidential computing. And we started 5 years ago, even before the term confidential computing was coined. But the idea that we started with was, how can we use technologies such as secure enclaves, privacy-enhancing technologies, to integrate seamlessly with the data pipelines that large enterprises have, the applications that they have, which they're now moving into public cloud, and how do we secure those applications? How do we secure the data associated with those applications, and enable new use cases where data can be shared between parties which don't really trust each other or are prevented from sharing data with each other because of certain regulations or data sovereignty laws, which are becoming increasingly common these days. Our vision as a company is that confidential computing will become ubiquitous in terms of availability of the underlying hardware technologies. We already see that confidential computing technologies is available from multiple chip vendors. It's also available in all the major cloud and public cloud today. It's available through various server vendors as well. So confidential computing technology as an infrastructure is becoming increasingly common. Then there are various ways to build applications using confidential computing and running them in secure enclaves. There are lift and shift approaches like Steve described with Anjuna. We also have a lift and shift approach. And there are also SDKs available from various providers. There are a lot of technologies available in the open source as well. And over time, it will also become fairly easy to build enclaves and take existing applications, run them in enclaves. At that point of time, we are looking at solving problems at a higher layer where you have your enclaves, but then how do you manage those enclaves at scale? How do you take them, deploy them in production? How do you enable use cases where you can build applications which were not even possible to build before, or solutions which were not possible without using confidential computing? How do you make sure that healthcare data, which is protected by regulation, or financial data, which is protected by GDPR and such regulations, can now become available to be shared with applications and with different users and be acted upon? And that's when we'll be able to utilize the full power of data and make it available to be analyzed and processed. The benefits of using confidential computing is that it's available in the cloud. It can be integrated easily with cloud architecture, with data services in the cloud, and that's when it becomes really useful. We believe that it will be available in the OEM hardware, in the cloud, and then once confidential computing becomes a default method of deployment of applications in the cloud, that's when end-to-end security of data will really become possible. So data is today protected at rest and in motion, but confidential computing takes it to the next level where data is also protected when it is being acted upon in use. And with confidential computing being able to deploy the workloads at scale and in production, that will close the loop of protecting the data throughout its life cycle. Some examples of confidential computing that we are seeing being deployed in practice today range from use cases in the healthcare to use cases in financial sector, and then the use cases in the government. And we'll see increasing number of use cases in other sectors as well, whether it be retail or other places where data is regulated or data needs to be shared and protected while being processed. And so here is an example of a press article which highlighted some of the use cases around confidential computing. Intel has been on the forefront with the Intel SGX technology, but then there are companies like Consilient which are pushing the boundaries using confidential computing to build better solutions for anti-money laundering. And then in healthcare, we see examples of institutions such as UCSF pushing the boundaries of confidential computing and using that to develop platforms for accelerating the development of AI algorithms. And I'll talk briefly about some of the use cases from these as well. This slide shows you a little bit more details around the use case with Consilient, where they're building an application for anti-money laundering. So today, there's a lot of money that flows through illicit and illegal transactions. The estimates vary from billions of dollars to trillions of dollars. And all of these flow through a shadow banking system and doesn't get, it's very hard to capture these transactions. So that's less than 1% of these transactions today are intercepted by law enforcement agencies. And what has been shown is that if you use AI technology, and then you can look for certain patterns in how the money is being moved across different institutions. There's certain signals you can get from just by looking at the transactions and who is making those transactions and the time of the day and various things. But to be able to do that analysis and to be able to run that machine learning algorithm, you need to have access to data. What has also been shown is a new technology in machine learning, the federated machine learning approach, where different parties participate and jointly run a machine learning algorithm. That has been shown to be very effective in detecting money laundering cases. However, banks in general value their data a lot. The data is sensitive and they're not really allowed to share data with each other. But by taking advantage of confidential computing, what Consilient has been able to do is they have built their machine learning algorithms. They've been able to deploy it in various banks which participate in the system for sharing data inside confidential computing environments. And then there are confidential enclaves, applications running inside confidential computing enclaves in various participating banks. And then the models that they create get shared with a central place, and then they get the average of those models can be taken and shared back with the participating banks. It's very important to protect the data in this case. It's also very important to protect the algorithm and the model that is created by the federated machine learning. And with confidential computing, what has been shown that a model can be deployed at scale. It is able to protect the data end to end. It's also able to protect the model, the intermediate model and the final model end to end, and prevents any of the participating parties to act maliciously or to tamper with the data or the model. Another use case for confidential computing is Beekeeper AI, which is a platform being built by the UCSF Center for Digital Health Innovation. What UCSF realized is that artificial intelligence is playing a big role in healthcare, and the team over there was the first team that built an AI algorithm that goes into medical appliances that got FDA approval. But being able to develop an AI algorithm that can be used in healthcare is very expensive, and it also takes a lot of time. This is because getting access to data that can be used for training as well as inference is very hard. Data is protected by HIPAA regulations. Also, data is protected by different data owners, which could be health care providers, hospitals, medical centers. They value the data very much, and they don't really want to share that data with anybody else without any benefit to that. But using confidential computing, what a solution has been built, which is called the Beekeeper AI Platform, which allows the data owners and the machine learning algorithm owners to all come together and be able to build a mechanism by which algorithms can run inside confidential computing environments, and the IP inside those algorithms can be protected. So the algorithm owner or the creator of the machine learning algorithm can be safe that their machine learning will not be stolen by somebody. And the data owner can also be assured that their data will not be stolen by anybody who's running an algorithm on top of the data. So by creating this, the platform using computational computing, it is estimated that the time it would take to get regulatory approval for building new AI algorithm will be reduced by 55 to 75%. And this will also lead to a cost saving of up to $2 million per algorithm. And as more and more algorithms will be developed in AI that go into diagnostics, into medical appliances, with the doctors, this will deliver tremendous benefit in healthcare, a lot of economic benefits to patients, and generally for the society. So that's the power of confidential computing and the platform that UCSF is building. I'll also show a demonstration of how confidential computing works in action in healthcare environments. And this is with the recorded demo that I'll play in a second. This was recorded a few months ago to look at X-ray images from lung X-rays, and they were analyzed inside confidential computing environment such that the X-ray images themselves were encrypted, and they were only decrypted inside a secure enclave. And then a neural network algorithm was run on top of the X-ray images to classify the images for having COVID or not having COVID. And what we'll also show in the demo is that if you did not use confidential computing, then sensitive data was available inside the data, inside the algorithm. And once you put the application inside a confidential computing environment, run it inside a secure enclave, then the data is protected. So with that, let me play the video.
This demonstration shows how confidential computing can protect AI applications in healthcare. Our input data is chest X-ray images used to detect COVID-19 disease and may contain protected healthcare information about the patient. First, we will use our encrypted image data outside of a confidential computing environment and show how this makes the data vulnerable in use. Next, we'll secure the workload in a trusted execution environment to prevent access to the data and the AI application while it is in use through in-memory encryption. Here we can see that our image data has been encrypted at rest and is shared securely as a ciphertext. After running our workload without confidential computing, we can perform a simple memory scraping attack using the process ID of the container. This creates a file called memory dump file, and when we interrogate this file, private information can be recovered from the memory used during processing. Looking through the memory dump that's been retrieved, we can see that there is an encryption key contained within the information, and there may well be private healthcare information related to the patient. Now we will run the same workload inside a trusted execution environment. The application functions in the same way as before, and we will implement the same memory scraping attack. This time we see no private information in the memory contents, ensuring our data is protected while in use. After creating the same memory dump file, we can examine the contents of the memory created by the trusted execution environment. The only plain text information is related to the implementation of the trusted execution environment, and this is non-sensitive and cannot be used by an attacker to access our data or the AI application code. The key that we saw before is not visible within the encrypted memory retained from the process. Now we can use the output of the AI application that was encrypted within the trusted execution environment and pushed to a safe storage location. We can download the encrypted file and see that the output from the AI application is again stored in the form of a ciphertext. Having secured the output data at rest, we can now decrypt it using a decryption key that is protected within a confidential computing environment. After decrypting the output data, we can see that the output of the AI application is the report that would be used by a data analyst to evaluate the accuracy of the model for diagnosis of COVID-19 from the chest X-ray images.
As demonstrated in the demo, confidential computing can be used to handle and process some very sensitive healthcare data and be able to get access to that data, run machine learning algorithms on that data. This provides tremendous value in healthcare, but also in other sectors like government and finance. What I want to leave you with is that confidential computing is real. It's available today. It's available to be used in production. It's available to be used at scale. And there are companies, there are organizations which are already using it at scale in the cloud and on-prem in various environments. Over to you, Steve.
Thank you, Anand. Both Anand and I are passionate about security, and I hope in this presentation we've encouraged you to take a look at the new security capabilities that exist with confidential compute and how you might take advantage of them in the confidential cloud. We also know that to secure more applications, we're going to have to make it easy so that people can take advantage of these primitives and work them into their application security. So as you look at your options, think about, how do you get broad application support? What applications are you using? Are you using ML? Are you using databases? Are you using web servers? Look at the application support. Look at how easy it is to deploy on the prem and in the cloud. Is the solution you're working for, does it need to be technology agnostic, or is it specific to a particular technology? Are you going to lift and shift applications? Are you going to modify your applications? Think through those things as you think about what you're going to work with and who you might work with. Think about your keys and your current security that you use. An awful lot of what happens in confidential compute is there are fundamentally different ways to bootstrap your security process, but then you want to continue to use good practices in terms of key rotation and management and data hygiene and what goes on there. So how do you integrate your existing IT processes and systems into what you're buying? And then think about the future. The hardware has launched really in 2015. As Anand said, there are organizations getting value from this today. You're not the first company to go through this or the first organization to go through this, but it is technology that is evolving. And so are the solutions we're looking at, how much work will it be in the future to accommodate new clouds, new platforms, new technologies that are coming forward? So thank you. Anand, anything you want to add, or I guess we open it up for questions?
I think there's a question.
Anand, go ahead.
I was looking at the question. There's a question on what's the overhead and CPU cycles for running in a trusted enclave. We have been running some fairly large applications inside enclaves, and what you're seeing with the latest Intel's third generation Xeon processors, the Ice Lake processors that we're able to achieve near native performance with less than 5% overhead of running the application outside the secure enclave, which means it's very good for large machine learning based applications. And this is a significant improvement from the hardware that was available previously. But with the newer hardware, I think we are ready to take on bigger workloads with minimum performance overhead.
I think if I could add a little bit to that, one of the important things to think about from a performance point of view is the isolation and the encryption is happening at hardware, and that's happening at memory access speeds. So that's not where the performance impact is going to come from. Where you'll get a performance impact is each of the technologies, whether it's SGX, whether it's SEV, whether it's Nitro enclaves, they have a barrier, and each one uses a different technology for managing that barrier. And so looking at how often your application has to cross that barrier, that's the place to be careful and look at the technology and how it helps you with that.
Great. We have a couple more questions. And so the next one is, how do you get around the extremely limited memory space of SGX? Redis fits, Oracle does not. Any comments or perspective on that?
With the newer Ice Lake processors, the memory limitation of SGX has significantly been relaxed. In the previous generations, you're limited to up to 256 MB of enclave page cache or EPC in SGX. With Ice Lake, that is relaxed to hundreds of gigabytes of EPC. With that, what we are seeing is very large applications which had severe performance overhead because of the memory usage. They now fit inside the enclave and they work fine. I would still be a little bit wary of running commercial applications like Oracle inside a secure enclave, because apart from using a lot of memory, it also does a lot of other things native to the CPU that may not make it amenable to run inside an enclave. But there are a vast number of other applications other than databases, and we are seeing a lot of machine learning algorithms, for example, that work very well inside enclaves.
Even before Ice Lake and SGX having a relatively limited EPC size, the enclave protection space, how big you could make it, you could still virtualize memory and bring it in, but obviously as you're virtualizing memory, it's got to be encrypted as you swap pages in, it's got to be decrypted as you swap pages out. So large applications that consumed a lot of memory definitely had a performance impact for dealing with that virtualization. And as Anand pointed out, with Ice Lake, the latest generation of SGX hardware, you can create enclaves as large as a terabyte. And so we were able to test the performance there and understand the implications that has, which obviously opens up a significantly larger set of applications that run in SGX. SEV and Nitro enclaves have different restrictions in terms of, or different performance characteristics. So you can run very, very large applications in confidential compute today, but when you engage in this process, it's worth talking to somebody who's been through it, and they can help you identify what's going to be easy and where some of the challenges will be.
Great, thank you. And so to everybody, please enter more questions. We're eager to get your feedback. That's awesome. And a couple other questions. How can I test this stuff out? Where can I get started?
Happy to answer that one. We have a demo environment. Some people struggle to get their hands on the hardware. And so we'll make a demo environment available to folks, give them a script to run through where they can bring their own application and play with it. And in that environment, it's easy to touch this stuff and see what it actually does and how it works for your workloads.
And I can answer that as well. So there are two parts to it. about where you run the applications. You need the right hardware to run confidential computing environments, and these hardwares are now easily available in the Azure Confidential Cloud. They're available in IBM Cloud, and then if you go beyond Intel, then SEV machines are also available in GCP and Azure. AWS has Nitro enclaves, so that's another platform for confidential computing. But then to build your application, deploy them in these various cloud environments, we provide a SaaS platform called Confidential Computing Manager at ccm.fortanix.com. Anybody can create an account. We provide a free trial right now, and they can start building enclaves, deploying them, using them.
That's great. And then which applications do organizations typically start with? Where are you seeing the traction and kind of the business criticality? Where does that hit?
We are seeing a lot of applications that do machine learning. In addition to that, applications which are acting like a client to a database containing encrypted data. So being able to decrypt data read from a database and provide it to an end user, encrypting and decrypting data on its way. That's another use case for us. We are seeing applications in the sectors where there are a lot of regulations around data protection, like HIPAA, GDPR, CCPA, and how do you enable data sharing in those environments? How do you enable compute of data brought in from multiple parties? And those are the problems we are solving, and we are seeing that confidential computing is attracting a lot of use cases in those areas.
We're seeing a lot of similar use cases. Multi-party compute is obviously a place where there's an awful lot of talk about homomorphic encryption to get multiple parties to be able to interact on a common data set. But that has, about 1,000,000 to 1 performance impact, whereas confidential compute has virtually no performance impact relative to that. And so we're seeing a lot of use cases where people are doing AI work and one person owns the data, one person owns the model, and how do you set up a trusted environment for that to work? So that's one set of use cases. Distribution of secret information, whether it's certificates into your web services or web servers, or key management, key distribution, key localization. We're seeing a lot of use cases there. And then a lot of data processing components where people are caching data and wanting to cache the data close to the edge. So they're getting it out into the cloud, but they want to keep it secure where the big warehouse is locked away on-prem somewhere, and seeing applications that fit that ilk.
Okay. And then here's another question. How does confidential computing compare with other technologies for data security, like the homomorphic encryption and multi-party computation? You briefly touched on that, but if you could just give a little nuance, a little bit more insight on that.
So if I just start by defining what homomorphic encryption does, homomorphic encryption allows you to operate on encrypted data. So if I have 2 and I encrypt it, and I have a 3 and I encrypt it, I should be able to do an operation where the encrypted result ends up being the same as 5, just encrypted. So you never have to move something into the decrypted space. Lot of research going on in this space. I think it's very exciting. And there's neat things that are coming out of that, but it is computationally massively expensive to do that. But multi-party compute has a tremendous number of use cases that people are interested. The generic sample is somebody owns data. The example Anand did was the bank with financial information. Somebody else owns models. You've got a startup that's created a model for detecting fraud, for example, and somebody else is kind of the escrow company that will manage the compute for this environment, where you bring the two things together in a trusted space and do that. And confidential compute makes this possible in a way that really wasn't possible before, because you really can get to a zero trust environment where the only place data is decrypted is inside these enclosed boxes, doing their encryption themselves. So these use cases that people have wanted to do for a long time are now possible with the new security primitives that confidential compute brings to the table.
I'll add to that. This is not an, I don't consider it as an either or question. I think homomorphic encryption, multi-party compute, confidential computing, these are all various ways to do data protection. And as a customer, as a user, when you're trying to secure your data, you are looking at all of these things, and then you consider a few factors, such as what is the performance impact. Steve touched upon the massive performance difference between confidential computing and other technologies. But then there are other things like what's the security model, what's the ease of use or the ease of flexibility of deployment, and what's the scalability, or whether you have to change your applications and your deployment architecture or not. Right now, confidential computing provides a lot of advantages over existing technologies in terms of ease of use, ease of deployment, much better performance, scalability, and it's ready for production use. These hardware devices are available everywhere in the cloud. The technologies to build enclaves are available, and the technologies to manage and orchestrate applications and building workflows, they're all available right now. As the technologies for homomorphic encryption mature, maybe for some use cases, they will become more competitive or better suited. But still, there may be an opportunity for confidential computing and other technologies to work together, where confidential computing can provide hardware assured integrity of the components which are inside homomorphic encryption, or it can provide ways to secure encryption keys and other aspects of the overall solution.
Okay, awesome. Thank you. And then how does confidential computing help with meeting compliance requirements like GDPR, CCPA, and others?
What we are seeing is that even regulators are starting to recognize trusted execution environments in confidential computing. One example of that is the German government brought up a regulation saying that the healthcare information for their citizens need to be processed inside a trusted execution environment. And the way it has been interpreted by the industry is that you need to use technologies like confidential computing to achieve that and process the data inside the trusted execution environment. We are seeing a lot of use cases where customers are looking to use confidential computing to achieve HIPAA regulation. For example, the UCSF use case I talked about. The whole idea is you can get regulatory approval much faster if you use confidential computing compared to not using confidential computing at all.
And that's where we see activity as well, is customers using the new security primitives of confidential compute to make it easier to prove to the regulators that they have a secure environment and they're meeting the intents of the regulations. The ability to show that you've encrypted in use as well as at rest and in motion is one of the checklist items now that people are beginning to think about and add to their security profile.
Yeah, I'll just add to that most of these regulations require auditability. So with confidential computing, you can audit reports which are tied to the CPU identity and the identity of the application that's running. And that is very important and very useful to achieve regulatory approval and to achieve compliance for these various regulations that are coming about.
Okay, excellent. Well, thank you so much for the answers and the perspective and insights. This is fantastic material. And any last thoughts to conclude our webinar?
To me, confidential computing will be prevalent, ubiquitous in the next 5 years. But the time for adopting confidential computing is now. Confidential computing environments, hardware, they're all available readily if you want to use them in the cloud or on-prem. There are various ways to build applications that can easily be deployed in confidential computing, and a lot of very important use cases around achieving compliance, around securing your data pipeline are being enabled today with technologies which are already easily available. So I would encourage customers, companies, organizations to go look at confidential computing and start using it.
I agree. The hardware which enables confidential computing has been available now since 2015, 2016, depending on which vendor you're working with. In 2020, every single major cloud vendor announced a confidential capability. So you can now access this hardware on-prem by buying machines, and you may actually have machines already. And you can access this in any of the major clouds at this point. And it brings some very important capabilities to the table to help secure applications and make the world more secure. And so encourage people to take a look at all the options that are out there, and know that you don't have to be a trailblazer at this point, that this technology is here and it's available today.
That's great. So a little bit of housekeeping. We wanted to point out that this was the third installment in the series for confidential computing. We also had the confidential computing, why should I care? That was the first part in the series. We also had confidential computing, protecting data and use. So those are available at these URLs. And so this presentation will also be uploaded, and we really encourage everyone to rate the webcast. We really look forward to your feedback, any comments you might have. If you have additional questions, please let us know. The webcast and the copy of the slides will be available at Snea Education Library with the link shown there. We also publish a Q&A blog after the call. That's in a couple days, and that will have a written response to all the questions. And please follow us on Twitter to keep informed on all the next webinars coming up in the series. And thank you both to our presenters. Thank you very much for all the input and contribution that you had, and thank you to everyone who joined today. Thanks again, and have a great day. Thank you. Bye-bye.
Thank you. Bye.
Thanks.